Sunday, December 28, 2025, AGNDD IntelliReport topic. Scientists found a new state of matter between liquid and solid. Please pardon any visual and informational inaccuracies in this partially AI-generated article-based video. Scientists found a new state of matter between liquid and solid. This corralled, supercooled liquid relies on the surprising property that some atoms in a liquid remain stationary regardless of temperature. By Darren Orff, published December 26, 2025, 9 a.m. EST. Here's what you'll learn when you read this story. The manipulation of metals as they transform from a liquid to a solid can have immense benefits for technologies. A new study finds that the manipulation of stationary atoms in a liquid metal can alter the properties of the resulting solid, even lowering the temperature at which it cools entirely. The authors describe this new breakthrough as a hybrid form of matter that lies between a solid and a liquid. Understanding the atomic machinations of metals is more important than ever, as technologies of ever-increasing complexity must get the most out of rare earth metals. One of the most exciting areas of research right now is right at the line between a metallic liquid and solid. Typically, we think of matter in three forms: as a gas, liquid, or solid, sometimes plasma if you're into that sort of astrophysical thing. While we have a pretty good understanding of the properties of gases and solids, it's the third major form of matter, liquids, that still has the ability to surprise. In a new paper published this week in the journal ACS Nano, scientists from the University of Nottingham in the UK and the University of Ulm in Germany once again showed why many aspects of liquids remain perplexing mysteries. By performing transmission electron microscopy during the solidification process of molten metal nanodroplets, the scientists observed that some atoms in the liquid remained stationary, an atypical phenomenon, as atoms in a liquid typically mingle about like strangers lost in a crowd. The researchers were able to perform the experiment thanks to the sub-angstrom low-voltage electron (SALV) microscope at the University of Ulm, whose main mission is to study radiation-sensitive materials at ultra-high resolution via transmission electron microscopy. While most of the atoms in the liquid forms of the various metals did vibrate as expected, the scientists noticed that some stayed perplexingly in place. We began by melting metal nanoparticles such as platinum, gold, and palladium, deposited on an atomically thin support, graphene. Christopher Leist, a co-author of the study from the University of Ulm, said in a press statement. We used graphene as a sort of hob for this process to heat the particles, and as they melted, their atoms began to move rapidly as expected. However, to our surprise, we found that some atoms remained stationary. These atoms remained stationary and bonded to the support materials around a point defect. And by increasing the number defects using an electron beam, scientists could effectively control the number of stationary atoms in the liquid. This is a big deal because as a liquid turns solid, the number and position of the atoms within can directly influence the solidification pathway. If the stationary atoms are low, the liquid eventually solidifies regardless. But if the number is high, the liquid can actually be prevented from forming a crystalline lattice. This effect was particularly pronounced when the authors created a ring, or corral, of stationary atoms around a liquid and then dropped the temperature. Once the liquid is trapped in this atomic corral, it can remain in a liquid state even at temperatures significantly below its freezing point, which for platinum can be as low as 350 degrees Celsius. That is more than 1,000 degrees below what is typically expected. Andrei Klobostov, a co-author of the study from the University of Nottingham, said in a press statement, "Our achievement may herald a new form of matter combining characteristics of solids and liquids in the same material." Strangely, the liquid will still eventually solidify, not into a typical crystalline structure, but into an amorphous solid that is highly unstable. Once the ring of stationary atoms is disrupted, this unstable solid forms a normal crystal. The authors note that this breakthrough could help transform the use of rare earth metals in clean energy conversion and storage, while also allowing for significant improvements to platinum on carbon catalysts that are often used in fuel cells. Darren Orff, contributing editor. Darren lives in Portland, has a cat, and writes edits about sci-fi and how our world works. You can find his previous stuff at Gizmodo and Paste if you look hard enough.
Thank you for watching this AGNDD Intel I report, dear viewers. Please like, subscribe, and click the bell button to get notified during new uploads. And make sure to tune in next time. Stay safe and healthy. Cheers.